confused. So what I intend to do is really step back and talk a little bit about what is passive intermodulation testing, and then work my way towards answering the question at hand, which is, once I understand the test, then what frequency band test set should I use to perform this test? So starting at the beginning, what is passive intermodulation, or PIM? Well, PIM is interference. It is noise that's being generated by the transmit signals to the cell site when they encounter nonlinear junctions in the RF path. And so if you look at the diagram that's shown above, what the two red arrows are representing multiple transmit signals at the cell site, and the blue lines are representing the passive intermodulation frequencies that are being created by those red frequencies. So as we transmit the red frequencies through the cell site, the intent is for them to go through and nothing else be created. But because of these nonlinear junctions or nonlinear materials in the RF path, we get a mixing of those frequencies and creation of all these other frequencies. And the thing that's important to remember is that any of those frequencies could be an interferer with the receive system, one or more of the receive systems sharing that RF infrastructure. So I've thrown out a term here, nonlinear. I use it every day, but I wanted to stop back and make sure people understand what I'm talking about. We're talking about the relationship between current and voltage. And so if I'm looking at the connection between two metal objects, if I have high contact pressure, or if those metal surfaces are welded together or soldered together, I have a very linear relationship, that as I increase the voltage, the current increases in a linear manner. Contrasting that, if I have something that's acting in a nonlinear fashion, it means that the relationship is not linear. So if you look at the graph at the lower left, you can see I have something that looks like a squared relationship, that as the voltage is increasing, the current is slowly increasing, then something happens to cause a rapid increase in voltage. So things that can cause that, if I have two metal surfaces that are just lightly contacting each other, that can be a source of a nonlinear junction. If I have oxide layers on the metal surfaces that are preventing a good metal-to-metal contact, you can have things like electron tunneling, all sorts of interesting effects that are causing this nonlinearity. Also, if the surfaces are just misaligned, it means that in some places I may have a good metal-to-metal contact, and in others I may have a complete separation. And in that in-between zone, I may be having small micro-arcing, or I may have lightly varying contact surfaces. So those are all the kinds of things that when I talk about nonlinear junctions, keep in mind this is what we're talking about. We're talking about a relationship between current and voltage, and as you'll see as we go further, it's very often caused by metal-to-metal contacts. So at a cell site, what are some typical sources of nonlinearity? Well, as I said, loose metal-to-metal contacts are probably the ones you're going to experience most often. That can come from poorly terminated RF connections. It can come from metal flakes inside of the connectors, that if you were terminating those RF cables and didn't do a good job of cleaning out the metal flakes, and they're left in the assembly, then they're going to be in there floating around and potentially causing these nonlinearities. Loose RF connectors. I can't count the number of times I've gone to a site to perform PIM testing, and before I do anything, I just reach up and see if I can turn by hand the RF connectors at that site. And you'd be surprised how often is the case that the connector right at the radio, the last person who had worked on that site, never took a wrench and tightened that connection. And that can be the source of these, or causing the nonlinearity, which is causing this PIM. Metal flashing on rooftops. Well, now we're talking about things that are outside of the antenna system itself, and things potentially out in front of the antenna. That loose metal-to-metal contacts or nonlinearities external to the antenna system are just as much a problem as the things inside the antenna system. Once again, it depends on how much power is hitting them and the voltages that are occurring, but external PIM problems are rampant in the industry today. Loose rivets, screws, etc., that's mostly inside of components. So if I have an antenna that someone has damaged during installation, or it saw a lot of shock and vibration in getting to the cell site, you may have loose components inside the antenna that, even though it was passing when it left the factory, it may no longer be passing by the time it's been installed on the site. Now, those are all metal-metal contact related issues. You know, rusty surfaces. You know, PIM has been long referred to as the rusty bolt effect. Well, rusty surfaces in front of an antenna can be sources of this nonlinearity. Then you get to nonlinear materials. Magnetic materials in particular have an impact on the BH curve as opposed to the voltage versus current curve. So if I have a material that's going to have a nonlinear relationship between the applied magnetization and the magnetization that remains in the material, or the remnant magnetization, that can cause a nonlinear effect. So these are all things that in a cellular environment are the types of things that are causing or the nonlinearities that are the sources of the ultimate PIM that we're here to address. So why do we care? Well, the graphs, the pictures above is actual data showing, you know, some noise rises that you can get within the system if the nonlinearity is bad enough and if the frequency combinations are such that the intermodulation product falls within the receive band of the system. And if that occurs, then you end up with dropped calls, access failures, slower data rates. In general, it means you have unhappy customers, that the system itself is generating interference that's competing with the users who are trying to use that system. So how can we eliminate PIM? Well, I wish there was a magic PIM wand that you could wave and make it all go away, but in reality you can't. You cannot completely eliminate the passive intermodulation. But what we can do is we can reduce it to a level that it's no longer causing a harmful interference to the systems that are trying to use that RF infrastructure. And how do we do that? Well, we improve or eliminate the PIM or reduce the PIM by improving the linearity of the system. And now what's shown in the picture above is that if I look at the arrows, you know, one of them is showing a beginning linearity, and it shows that I drive the linearity down, and you see all these intermodulation products are decreasing as the linearity of the system is improved. And this actual picture is representing the PCS block of the 1900 megahertz system in the United States. And if you notice, if I'm an A block operator running in a PCS system, the intermodulation product that actually falls in my band is IM11. So by reducing or improving the linearity of the system, I drive not only IM3, IM5, but I also drive all the intermodulation products down. And the concept here is if I can drive them to the point where they're below the noise floor in the range I'm trying to measure, then I've now taken what was a harmful intermodulation product and turned it into a non-harmful product. So how do we measure linearity? Well, we inject two unmodulated test signals of a known magnitude into the system, and we measure the third order intermodulation product. IM3, or the third intermotor intermodulation product, characterizes the linearity of the system. In other words, if IM3 is low, the linearity is good. If IM3 is high, then the linearity is poor. And I've struggled on where to put this slide, but I've decided just to throw it in right here. This test is not only just a pure linearity test, it's something also that's used to verify that the linearity is not something that's going to be changing over time. So PIM testing is a dynamic test. Dynamic means with movement, which means that while we're performing the test, we need to be lightly stressing the connections and the components to make sure that they're not going to change over time or change over the stresses that are naturally going to occur due to wind, vibration, thermal cycling, etc. The most common or most practical method of stressing components is either a tap test or a flex test. I would highly recommend that you consult with your operator or who you're performing testing with to get more detail on what they prefer. The idea here, once again, is that if the IM3 is stable while being subjected to movement, then the construction is robust, which means that that system is going to be reliable, during for the long term. Okay, so back to the frequencies. So why IM3? Why not IM2 or IM5 or some other intermodulation product? Well, IM3 is very high magnitude. So with typical frequencies that we would see during in a system, the magnitude of IM3 is at a high enough level that we can accurately measure it. So that's one of the reasons for measuring IM3. There's also some practical reasons that IM3 is physically close to the frequencies that you're starting with. These intermodulation products are mathematical combinations of the frequencies, and so therefore if I just do the math, whatever the separation is in hertz between F1 and F2, that's how far away IM3 is from either F1 or F2. So it's practical to create a test scenario where I can transmit F1 and F2 that'll pass through the system I'm testing, and IM3 can fall in band and be received by the same system. So it's just a practical frequency to be measuring. And then also, by choosing a single IM product and using that as our measurement point, it provides a way for us to standardize within the industry to compare linearity. Now that's comparing linearity at a component level. It can be comparing different components from different manufacturers, and it allows operators to compare the linearity of different sites. So the most common question I get after all of this is, but wait a minute, IM3 doesn't fall in my own band. So most people will understand, okay, I'm going to measure IM3, and then they look at their actual licensed frequency block, do the math, and say, but wait a minute, it's IM5 or IM7 that falls in my band. Why am I not measuring IM5 or IM7? Well, this is a repeat, but it's to say it again. PIM is not a direct measure of your system noise level. It's not like a sweep test or an isolation test where when I'm transmitting and looking at the reflections in my system, I'm actually seeing the performance of my exactly, how the reflections are going to occur in my system. With PIM testing, you are measuring the linearity of that system, and you're doing it in most cases in an indirect method. So we measure the relative linearity of the system by using a very controlled test to do it. And as I said before, we measure IM3, and so therefore we're going to transmit frequencies that are going to generate IM3. So it's not really relevant whether or not IM3 falls in your specific frequency block. We're still going to use IM3 as a common method to measure the linearity of the system, with once again the understanding that if I can control IM3 to a known level, I'm also reducing all of those higher order intermodulation products and driving them below the noise floor of the system. All right, so now I'm 11 slides in. I'm finally now starting to answer the question, well, which test frequencies should I use? There's a lot of different test equipment out there. There's, each manufacturer has multiple frequency bands available for each of the different systems. And unfortunately, it's not a simple answer. Otherwise I wouldn't be having a 45-minute discussion about this subject. What is going to what's going to impact the exact frequencies you use is impacted by several factors, and that's what the remaining slides of this presentation are going to address. And what you see in red here, this is going to repeat many times through the remainder of this presentation. Check with your customer. Ultimately, your customer is responsible for communicating to you what frequencies to use while performing this test. Now, if you are an operator paying attention to this, hopefully I'm going to provide enough information that helps you in coming up or understanding how to create the list of approved frequencies to provide to your customers. Now, I will say there is not going to be a chart at the end of this that says here are the correct frequencies. If you want suggestions, I'd be happy to entertain those. But also, I'd like to say that most PIM test equipment manufacturers, as a default or factory reset, will have frequencies that are appropriate for the band that you're testing. So Once again, always check with your customer, but if you get confused and are looking for something that's safe, generally the factory the default values for a given band are going to be a safe bet. All right, so I'm going to divide up the factors that are impacting the selection of frequencies into what I'm going to call internal factors and external factors. Internal factors are those that are because of the characteristics of the test instrument, and external factors are things that are related to the system that you're testing. So the first internal factor is the test equipment itself. If you look at the block diagram above, this is a fairly well understood diagram of how a PIM test works, where I generate two transmit tones, I combine the two transmit tones, and I send them out into the world to test whatever device it is that I'm testing. And that the IM3 frequency that I'm trying to measure is generated in the device under test, comes back into the system. The first component it's going to encounter is a duplexer to separate that transmit, or separate the incoming receive IM3 signal from the transmit signals that are passing through. That duplexer, or the front-end filters of the PIM test equipment, are really what is going to establish the frequency range that that test equipment will be able to support. We need to have a very high isolation duplexer because we're trying to measure a very low magnitude signal in the presence of very high magnitude signals. So the isolation has to be extremely high. We also are trying to keep the unit physically small, and so the combination of trying to keep it small and trying to the requirement that we have this high isolation means that that front-end filter has to be designed for a specific band, the transmit signals that will be allowed to pass, and a specific band of received signals that will allow to be received. So the PIM test equipment itself, that front-end duplexing filter, is going to be the first internal factor that's going to limit what transmit frequencies you can use and what IM products you're going to be able to receive. Okay, now that said, once I am within the range of that particular system, I have to be able to space the two transmit signals far enough apart in order to make that IM3 signal fall within the receive band of the signal. If you look at what's shown above, the math works out that whatever the frequency separation is between F1 and F2, that's how far away F3 is. So you can see that if I start moving F2 closer to F1, IM3 also starts to become closer to F1. So I physically have to space the two test frequencies far enough apart so that the IM3 that we've previously discussed and decided that's the thing we're going to measure to standardize to measure linearity, we have to make sure that it falls within the receive band, or the receive bandwidth of the test instrument. Another external factor, or now we're getting into the things that are not within the test instrument itself, but due to the system that you're testing. In order to perform a PIM test, or this linearity test, we have to be transmitting two transmit signals all the way through the system. If anything in the system blocks one or both of the transmit tones, we're now no longer performing a PIM test. So in the example above, let's say, for example, that the TMA, for whatever reason, passed one of the transmit frequencies but blocked the second transmit frequency. It means that we could measure PIM all the way up to the point inside that TMA where the blockage occurred. But beyond that, where only one transmit tone is passing, we may cause arcing, but we're not going to be able to excite the nonlinear junctions because we're only transmitting one frequency at that point. So the requirement is that the test system that you're measuring, the transmit frequencies that you choose, must be able to pass all the way through the system and not be blocked. Likewise, the IM3 signal that you're trying to measure has to be able to make it back to the test set. So, probably the most common problem there would be if there's a duplexer in the system, a component that's designed to separate transmit and receive signals. If you're transmitting through the transmit port and the IM3 signal you're trying to measure comes out a different port, well, that's not going to work. So make sure that the system that you're measuring has the ability for the transmit signals to go all the way through and for the IM3 signal to be able to make it all the way back to the system under test. Common components to look at. Look at the antenna. That's going to be one of the frequency limiting devices, any filters that have been installed in the system, or tower mounted amplifiers. A quick way to verify this is to perform a VSWR sweep test prior to performing your PIM test. This gives you assurance that the test frequencies that you're going to be using for the PIM test will be able to pass through that system. It also has the added benefit that it allows you to check and make sure that the system is just not broken before you start testing. It doesn't do any good to start your PIM testing if the jumper at the top of the system is not connected to the antenna, for example. So you want to find all of those problems, make sure that it's constructed correctly, that the reflections are at a minimum or acceptable for that system, and then perform your PIM testing. If you do come across something that's a frequency limiting device, then your only recourse in this case is going to be to bypass that component, and that means to put a jumper around it so that the test signals continue all the way through and bypass the component that you're testing. Now here we go again. Check with your customer. Don't randomly go out and start bypassing components. Talk to them before you do this and make sure that you have an agreement that that's an acceptable solution. Another external factor is external interference. The signal that we're trying to measure is generally a very weak signal. You know, typically IM3 levels in outdoor systems that we test are going to be verified down to a level of around minus 100 dBm. Now, the signals that we are measuring, the IM3 signals, are not only within the receive band of the test instrument, but they're also in the same spectrum that the mobiles are using to transmit to communicate to the base station. So it's very common to have, I'd say probably more common in an indoor system, but if I have mobile units that are trying to transmit and happen to be transmitting at a very high power level, their transmissions may interfere with the IM3 signal that you're trying to measure. So how do you do that? Well, a couple of options. You can either attach a spectrum analyzer to the system and monitor it and look and see if there's external interference at the measurement, the IM3 frequency you're trying to measure. Or most PIM test equipment manufacturers have a mode in their system that either will be a spectrum monitoring mode or a noise floor mode that allows you to look at the spectrum you're trying to measure and make sure that there's not external interferers coming in at that frequency. If you do experience external interference, you have several options. One is, as you remember, as I showed on the slide before, you can move the IM3 frequency by moving the transmit frequencies. So if you adjust the IM3 frequency slightly, you may be able to move it to clear spectrum to perform your test. The other option is if it's just broadband noise that you can't move the frequencies and get around, you may have to transmit into a low PIM load. This allows you to certify the construction of the site, but it does not allow you to look at the antenna radiation or things external to the antenna. Another option is increase the power. Now, all of these things are things that you, once again, you need to talk to your customer before you randomly start changing frequencies, bypassing components, transmitting into loads, or changing the transmit power for the site test. All right, so what if multiple test sets meet all of the requirements that I've just mentioned above? You know, that's actually very common. So in the North American frequencies, for example, if it's an antenna system and the antenna is the frequency limiting bandwidth, you know, the low frequency ports of antennas generally are designed to operate from 698 to 896, meaning that they'll cover both the 700 megahertz as well as the 850 megahertz spectrum. Likewise, the high band ports on most antennas will cover from 1710 to 2170 megahertz, covering the PCS as well as the AWS spectrum. Now, there's also new antenna systems that are capable of operating from 1710 to 2690, so that they're able to cover the 2.6 gig systems as well. Indoor systems, you need to be able to pass everybody's signals through those. So a DAS system, for example, you could meet the requirements from the ability to transmit signals all the way from 700 megahertz up to 2.2 gigs. So it means that any of those test instruments are potentially ones that could be used for that testing. Now, I don't have it here, but I probably should have had it. Once again, check with your operator. Most operators that I've spoken with will allow you to use either of those test sets, but that is, like I said, an operator decision. So as a continuation of that, to add more detail, let's break the test into two separate components. As I said before, you're doing a dynamic test to look for stability of the IM signal. You're also doing a magnitude test to make sure that the magnitude of the IM is not at a level that's going to cause interference. So let's address the dynamic portion first. When we're doing the dynamic testing, we're looking for spikes, and those spikes can be 10 dB, they can be 50 dB. So the magnitude of the spike is really not what's critical. The fact that it is spiking when I'm stressing it, that's the problem. And you'll find that just about any PIM test set is capable of performing that test. So it doesn't matter if I'm doing the dynamic testing at 700 megahertz or doing the dynamic testing at 1900 megahertz. Either one of those is going to be successful for finding loose connections. So if I now start talking about the magnitude and what's going to impact the magnitude, I'm going to say it straight out. IM3 is going to vary over frequency. Or another way of saying that is the linearity of the system is frequency dependent. Now, we in the PIM testing equipment business will tell you it doesn't vary a lot, and that's a generally true statement, that if I am using a single test set and varying the frequency within a single band and measuring a single PIM source or nonlinearity, the frequency, generally speaking, is fairly flat. Okay, so that is a true statement. However, what you'll find is that if I'm going over wide swaths of spectrum, that the variation in frequency is not something that's necessarily a small variation. And that can be due to the type of defect. Things that are the rusty bolt type problems are going to behave differently versus frequency compared to microarcing, and they're going to behave differently versus frequency compared to the ferromagnetic effects. Also, as you change frequency, you're changing the RF skin depth, so you can get different responses. So if I have a low frequency, I'm going to be penetrating deeper into the metallic surfaces than I am with a high frequency. So if there are plating contamination issues or nickel underplating, I may have very different responses at low frequencies compared to the response that I'm getting at a higher frequency. I also, when I'm radiating through an antenna, the radiation patterns out of that antenna are going to be different versus frequency, and it comes down to the electrical length of that antenna. A good example is an indoor antenna where, let's say, for example, I have a small indoor antenna. The back plane on the back of that antenna is some number of wavelengths at the high frequency. It may be less than a wavelength at the lower frequency. That's going to control how much radiation goes out the back of the antenna compared to how much goes out the front of the antenna. So you may end up with very different results measuring over the different frequencies just because different things are being illuminated by the different frequency bands. Then there's also the impact of insertion loss and also the radiation losses that are coming from those frequencies. So, if I'm doing PIM testing at 2 gigahertz compared to PIM testing at 700 megahertz, I'm going to have very different energy levels hitting the potential nonlinearities in the system. So once again, you need to check with your customer on how we're going to do this. The next slides are going to give some idea of the magnitude. So I'll have to say this is not an exhaustive study, but it is fairly representative of what I've seen. And what this chart is showing is PIM measurements taken using 4 different test sets on 4 different components. 2 of them are PIM standards. In other words, they're devices that we used with the intent of trying to generate PIM. And 2 of them are cable assemblies, actually constructed using slightly different variations. But as you can see, the PIM standards, the things that are constructed with a diode inside to intentionally generate PIM, across the full frequency spectrum, they're varying between 12 to 15 dB. as far as the magnitude of the PIM that's generated, or the magnitude of the IM3 that's generated by the particular nonlinearity. And when I look at the two cable assemblies, I'm getting 7 to 8 dB of variation between the two cable assemblies. Now, something that's also interesting to note here is it's not always a foregone conclusion that the low frequencies are worse than the high frequencies, because if you look, for instance, at cable assembly number 2, minus 72 dBm at 700 megahertz is the worst case position, whereas the cable assembly above it at AWS frequencies was the frequency that was the worst case frequency. So unfortunately, there's no specific way to say that, you know, a particular frequency is always going to be worse than another one. Now, it is interesting to look, if I look at the, you know, the difference between measuring at 700 megahertz and 850 and looking at that and comparing it to the difference at PCS and AWS, you'll notice that the variation across, in this case, you know, 133 to 140 megahertz is much less than the variation that you're seeing across, you know, over 1,000 megahertz. And that makes sense. I think if you did enough sampling, I don't think you would necessarily see a statistical difference that says AWS and PCS are always closer than 700 and 850. I think in the long run, I think these would all average out. My experience has been, you know, within those two bands, I would expect to see something on the order of that 4 dB variation. And in across the bands, 10 dB variation is probably something that I would say is very, very typical. Okay, this one is another one I find very interesting. It's going to take a little bit of explanation, so bear with me on this. This is looking at purely the impact of insertion loss on what you perceive as the measured PIM at the system you're testing. And so what we've done in this case is I'm looking at the difference of what a known PIM source, and so in this case it's a minus 80 dBm PIM source that if I measure it at the equipment, and let's just assume that on all of those pieces of equipment, it measured perfectly minus 80 dBm when I measure it directly at the test set. And then I put an insertion loss. You know, in this case, we're looking at 150 feet of 7/8 inch feeder cable. If I put that minus 80 dBm PIM problem at the end of that feeder cable, what's the change that I'm going to be experiencing from measuring it at the test set? This also assumes that the change in PIM versus power is the theoretical level of minus 3 dB for every 1 dB in test power. So if you think about this, the transmit signals are going to be attenuated by the insertion loss of the feed cable before they hit the PIM source. The magnitude of the power has been reduced. I'm going to apply that 3 dB for every dB change in power. The PIM that's generated is now reduced because the power hitting it has been reduced. Now the IM3 signal, going back to the test instrument, will be further attenuated by that same insertion loss. So in this scenario, there's a 4x factor of 4 times the insertion loss is what the change in measured IM is for this known minus 80 dBm system. So, and if I look at this now, and what I did in this case is I actually went into the manufacturer's data for AVA 5-50 and did linear interpolation to say, okay, for the average transmit frequency, what is the dBs per meter or dBs per 100 meter, and then for the IM3 frequency, what is the dBs per 100 meter, and did the math. And so I can show the calculation of how much insertion loss versus frequency occurred in getting to the PIM source, what the reduction is based on that 3 dB for every 1 dB change in power, and then looking at this insertion loss of the IM3 signal going back, and then calculating what the total loss in PIM is. So what's interesting here is that same minus 80 dBm PIM source, or that same nonlinearity, just by placing it at the end of the cable, you can see that by which test system I use, whether it's a 700, an 850, a 1900, or a combination 1900, 2100, you can see that the magnitude of the measured PIM at the test set is going to change. So across those 4 test sets alone, and just assuming this 150 foot of cable, there's a 4.5 or 4.2 dB difference in the magnitude caused only by the insertion loss of the system. And you can imagine that if I have a DAS system or something with a much higher insertion loss, that number only increases. Whoops, jumping ahead of myself. Sorry about that. Let's go back to where I wanted to be. All right, now we're there. So now the real question is, I probably have horrified a lot of you with saying that, you mean I can get 10 dB difference in PIM level, to be, whether I'm testing with one test set or another, and 3 dB here, 4 dB there. 3 dB and 4 dB and 10 dB is a lot of variation. If I'm trying to measure return loss, for example, I certainly can't live with 10 dB variation of the measurement itself and proclaim that that's good. So what about with PIM testing? Is that variation acceptable? Does it matter? And so let's look at a typical pass-fail system, and let's take a big assumption. And the big assumption here is that higher order modes are going to decrease by approximately 15 dB compared to the previous higher order mode. That is a very conservative estimate. I'd say probably things that are very nonlinear are going to behave like that. Things that are only slightly nonlinear are probably going to be closer to 20 dB reduction for each of the higher order modes. But if you take that assumption and say, I'm going to try to drive IM3 down to a typical minus 100 dBm type of a level, and make the assumption that IM5 is going to be, if I do that IM5 will be at minus 115, IM7 is minus 130, and IM9 is at minus 145, and then ask the question, well, if the PIM is varying plus or minus 5 dB, do I care? And I think what you'll see is that for IM3 and IM5, if those are the intermodulation products that are falling in your receive band, then that's probably a significant variation. And what that means is that you really should be measuring using test equipment at the frequency where those IM products are falling. So if the IM3 is being caused by 2 PCS tones, then you should be doing your testing on that system using a PCS test set. On the other side of that, if it's IM7, IM9, or some other higher order mode, which is the PIM product that's naturally falling in your band, what it's saying is that plus or minus 5 or even plus or minus 10 dB variation really doesn't make a difference. You're still driving by taking and measuring IM3, driving it down to a low enough level that even if you have plus or minus 10 dB variation over frequency, it still says that the actual magnitude of those 5th, 7th, 11th, etc. products is still below the noise floor. So we've achieved the goal. So in that case, it really doesn't matter what frequency band system you're using to perform the test. It's going to help you find and reduce the IM3 level, in other words, improve the linearity so that your system is going to be passing. All right, so I get this question a lot also. All right, so great. I'm working on a DAS system, and I only want to buy one piece of test instrument, or I'm a cable manufacturer and I really don't want to have to buy 5 different bands of equipment in order to perform this test. If I only have to buy one, what do you recommend? And this is my recommendation. My recommendation is, based on all of the factors I've discussed, I think on the average the lower frequency is more likely to cause the highest PIM than the higher frequencies. Now there's a lot of variables that go into that, and if we look long enough and hard enough, we're going to find exceptions to that rule. But I think in general, the things that are causing variation, that the lower frequency test set is more likely to identify a problem in the long run compared to the higher frequency test sets. But once again, verify that with your customer. Your customer is ultimately the one paying for this test and is ultimately the one who is going to specify which test equipment you use. All right, so in summary, PIM testing is a linearity test. And I've tried to say that over and over again, but it's the thing that even after you leave this presentation, you're going to forget it. So let me state it again. PIM testing is a linearity test. we measure the third-order intermodulation product to characterize the linearity of the system. It's not a direct measurement of the noise of your system. It's an indirect measurement. That we do recognize that by reducing IM3, we're improving the linearity, and we are driving those higher order products to a lower level. The test frequencies that you use must be able to pass completely through the system under test, and it must be within the capability of the test instrument to produce the tones and to measure those signals. As I said, from a recommendation, the lowest frequency band is typically going to be the worst case one for the systems you're testing. If the IM3 or IM4 product that fall in your band, in that case, I would recommend that you measure using that specific band. And then, once again, as always, verify the test frequencies with your customer before making any changes or any testing at a site. Okay, and that's it.
And now we'd like to take any questions from the group. Emilio, I believe you're on the line. Do you have any questions queued up?
I do have a couple. Well, actually, there's one that a few folks have asked. They've asked about the availability of the slides.
And I'd like to announce that the slides will be posted on the RCR YouTube page in about 1 hour after this meeting.
Okay, thank you. Let's see. There you go. So let me get started here. Going through the list. Get a whole bunch here at the end. Okay, Tom, would you always PIM test an entire system, or would you also do it in sections at a time? Is that a troubleshooting method?
The answer is obviously yes, and let's I'm going to address that on the macro network side, and then address it on the indoor testing side. On a macro system, there are fewer connections, and so it's probably safe to do component level testing to make sure, for instance, that your antenna arrived at the site without being broken. If you have a component that is historically showing problems and you want to make sure that it's not been damaged, I've seen customers who will specify or allow their installation companies to pre-test to verify that those components are good before you invest the time and energy into installing them on the site. However, on a macro system, if you're using proper techniques and if you're starting with good components, it's fairly common to come in and do it as a final pass-fail test. Contrast that with an indoor system. An indoor system has hundreds, if not thousands, of RF connections, and trying to inspect the quality in after it's done is quite frankly a mistake. And so the best solution for indoor systems is to work from the antenna back to the system. Verify that the antenna location is good. Verify that the individual branches are passing. Once you have passing branches, build those into together and work your way back towards the system. So absolutely, PIM testing is a test-as-you-go solution for indoor systems. I have to say I recommend that also for macro testing, but you have less risk on a macro system as long as, like I said, you're using proper techniques.
Okay, and then here's another question. Does the test power, either 20 watts or 40 watts, matter? And I guess you can probably expand that on beyond those two choices.
Yeah, absolutely. Test power does matter. That probably is another 45-minute discussion on what is the right test power. As I showed in the example, the theoretical variation is that the magnitude of PIM changes 3 dB for every 1 dB you change the power. So if I'm changing the test power, then clearly the magnitude of the PIM that's created is going to change. The PIM sources that I use that are a well-controlled diode, those tend to change closer to 2 dB per dB. things like, well, I'd say the jumper cables, the cable type defects, they're probably closer to the 3 dB per dB. So if you change the test power, there's really nothing wrong with that, except for you also need to change your pass-fail criteria. If you want to be using this linearity test to compare linearity between components or manufacturers or systems, and you change the power, then you need to plan on changing that pass-fail criteria to be appropriate for the power level that you're using.
Okay. List keeps jumping around on me. Hold on a second. And had a question on how are we getting IM3 out of the AWS band and the 700 megahertz band?
Okay, if you think back to the slide that I said you have to use frequencies that are necessarily outside of your licensed spectrum, that's how we're doing it within the 700 megahertz band. So I think if you look at the upper block and the lower block, I think it is possible in the lower block of 700 megahertz. If I go to the very far extremes of the licensed spectrum, I think I can create an IM3 that falls within the receive band. If I look at the 700 megahertz upper block, if I'm only using frequencies within the 700 megahertz upper block, it's I think it's IM5 or IM7 is the lowest order that will actually fall within your band. So what that means is that you have to choose guard band frequencies that are outside of your either the upper or the lower. You have to choose either if I'm if I'm Verizon and I'm the upper 700 megahertz frequency owner, it means that one of my test tones is going to need to be a guard band frequency within the AT&T or US Cellular or whoever the other license owner is for the lower 700 megahertz band. So that addresses the 700. For AWS, forget it. If I try to choose 2 AWS test tones, the best I'm going to achieve is IM17. So if I take, the lowest AWS test tone at 2110 and take the highest at 2155, that puts an IM17 that falls into the AWS receive. So you're never going to get IM3 by using an AWS only system. What is typically done in that scenario is, and quite frankly, if you have an AWS only system, the antenna port is going to be broadband, the coax is going to be broadband. It's really only going to be your tower mounted amplifiers that are going to be the issue. So if you want to verify the installation quality, put a jumper around your TMAs, and then you can either transmit 2 tones of PCS through it, and it'll still do the same, give you that same ability to measure PIM. It'll also measure the third order, or you can transmit 1 tone PCS and 1 tone AWS. That also gives you the ability to generate a third order intermod product. By doing 1 tone PCS and 1 tone AWS, you can generate an IM3 that falls in the AWS receive band. And that's probably the most common real-world problem with AWS spectrum. AWS by itself does not generate PIM that's harmful in its own receive band. Because of the 400 megahertz of separation between transmit and receive, let's face it, IM79 has such a low probability of causing interference that, if you're doing PIM testing on an AWS system, don't do it with the expectation that you're going to impact noise. Do it with the expectation that you're improving the quality of the system and the reliability of the system.
Amelia, we've got room for about 1 or 2 more questions.
Okay, we have a question on indoor transmit power. If it's less than 1 watt, do we need to PIM test?
Yeah, actually you do. I've seen some pretty amazing nonlinearities in an indoor system. I've done some testing recently where I've taken an indoor antenna and literally have tested with plus 30 dBm, which is 1 watt, and I've generated IM3 that almost saturated my receiver. which means I'm getting, easily with 1 watt, if I'm generating noise that's at minus 65, minus 70 dBm, then yeah, you're going to need to do that testing. I think one of the things that's particularly problematic about testing in the indoor environment is that, like I said, you have antennas that are with backplanes that are electrically short, so therefore the radiation is going all over the place, and you're necessarily putting those antennas near a lot of external metallic structures. And so the combination of that means that you have the capability of producing some very high magnitude PIM that even at levels that I've seen operators testing down at the plus 15 dBm level are still seeing PIM sources that are large enough that they can shut down a sector that's trying to run LTE.
And then there's been a couple questions here regarding the test set, if it has distance to fault, or I think as we call it, distance to PIM capabilities, and if you can discuss that.
Yes, the test sets from Anritsu all have distance to PIM capability, and what that means is that we use techniques that, just like distance to fault, that's used for identifying the location of reflections or location of impedance mismatches. We have the capability also to measure the location of where PIM is occurring. So that allows you to more quickly find and eliminate or find and improve the linearity of these systems. Now, it doesn't matter whether that problem is inside the antenna system or whether it's the roof flashing out in front of the antenna, the mathematics still works. So that's what we refer to as distance to PIM technology. And
do we have some more time, Jason?
Sure, one more question, Emilio.
Okay, let's see. Okay, I got a question from an earlier slide concerning the flashing. Is it any metal flashing, or does it have to be loose? And I think that has to do with possible PIM sources.
Well, yes, if I have just continuous metal in front of an antenna, let's say it's a perfect extrusion that's running 100% in front of the antenna, and there's no gaps and no separations, the metal itself doesn't necessarily cause the PIM. It's where I'm overlapping sections of flashing and I have loose metal-metal contacts, or it could be where I have sheet metal screws that are going through the through the flashing and it's lightly touching against something else. Those are the sources of the problem.
Okay.
Well, with that, I would like to thank
Emilio. I had one more. Okay, sorry.
Thank you for attending today's RCR webinar with featured sponsor Anritsu. This presentation will be posted to the RCR YouTube page in about 1 hour. Thank you for attending.